Okay, so it's time, 8:30. Today is the last day of the conference and third keynote speak by Professor Ninghui. Let me introduce Professor Lee's biography first. Professor Lee is a Samuel D. Conte Professor of Computer Science at Purdue University. Professor Lee received the bachelor degree from the University of Science and Technology of China, USTC. The special class of Gift Young in 1993. And a PhD in computer science from New York University, 2000. Professor Lee's research interests are now in the security and privacy. So Professor Lee has published more than 180 different papers. Professor Lee has received multiple best paper awards and test of the 10 paper awards in security and database. Professor Lee served as editor-in-chief of ASIACCS transaction and privacy and security since 2020. And Professor Lee has served in many leadership roles in research community, including the chair of the ASIACCS Special Interest Group of Security Audit and Control, ASIACCS, from 2017 to 2021. And Professor Lee is a fellow of both of the ACM and both IEEE. So today's talk with Professor Lee is titled Differentially Private Data Synthesis, State of Art of the Challenge. So please, Professor Lee, start. Please.
Thank you. Let me share my screen. Yeah. Thank you for inviting me and for the introduction. So I'm very happy to be here to share my thoughts on this research topic. So I guess there. So I'll open the chat window. So if anyone has questions, you can put here. You can also. There are not that many people. The audience is not that large, so feel free to interrupt if you want to discuss. So let's see. So I assume for this audience, I don't really need to argue for the importance of data in modern society and the importance of privacy, protecting privacy when using those data. So I'll jump right in, start by talking about differential privacy. So, so while we all agree that data privacy is very important, so it took the community significant time to reach a privacy definition that the community roughly all accept, which is differential privacy. So before differential privacy, a number of privacy notions were proposed. So among the more well-known ones are k-anonymity, L-diversity, and t-closeness. So the last one is my own work. So there were many others. So there was, I think people call it the alphabet soup of privacy notions. So that by itself illustrates that there's something kind of missing, not quite right in those privacy definitions. And differential privacy currently is most widely accepted. So this is the definition, and then I want to discuss why differential privacy is good. And I want to emphasize that the fact that differential privacy is the right definition for individual privacy doesn't mean that it can be applied everywhere and it will offer strong protection everywhere. So this is a formal definition, so introduced by Cynthia Dork and others in 2006. So this is a property of an algorithm. So we look at an algorithm that takes some input data set and then output something. So the requirement for the algorithm is that for any two data sets that are considered to be neighboring, we want to make sure that for any possible output T, the probability that on input D, the algorithm output T is not that much higher than the probability on input D prime, the algorithm output T. So in fact, the probability ratio should be bounded by this e to the epsilon. So it's very important to look at what the neighboring data set mean. So traditionally, when we look at the relational data sets are said to be neighboring if they differ by a single record. So there are two variants, whether you remove a record or you change the record to some other value. So there's some differences there, but that's not really important for this setting. So why is differential privacy good? Why does it make sense? So to answer that, let's first discuss why defining privacy is hard. Typically, when we talk about privacy, it means that we want to prevent the leakage of some information. So we want to hide some information. So we can call that as the privacy as secrecy. But in fact, this is hard to achieve. So this is an example that have been used in the literature to discuss this. So assuming that the society as a whole do not yet know that smoking causes cancer, say lung cancer, and somebody conducted the study, and then the study result demonstrate that. Now, before the organization is about to publish this result, a smoker Carl raised a privacy complaint. It says if you publish that result, then that will reveal new information about him. So people know he smokes, so maybe he posts on Facebook or whatever. But because the society doesn't know the linkage between smoking and cancer, so people doesn't yet know that he has a higher chance of getting cancer. But once the result of the study is published, then people know. So the moment we publish this result, people learn new sensitive information about Carl, and which can also potentially cause damage to Carl, so in various forms. So then the question is, can Carl complain that you shouldn't publish this data because publish the result of a study, because doing so compromise his privacy? And we want to emphasize that Carl doesn't even need to be in the study. So the study is performed on other smokers and non-smokers. The result comes from that. And this is just someone not involved in the study. So if we define privacy as secrecy, then Carl's complaint is actually legitimate. But if we take this as a legitimate complaint about privacy, then basically we're saying no data can be published because this is simply impossible to address all these privacy concern if we want to publish in the so-called privacy concern, if we want to publish data at all. So the problem is caused here by association. So the information we want to hide may be associated with some other public information. So then publishing this data may cause new information to be leaked. And if you go down that path, then you can never have a good privacy notion because there are all kinds of possible information association. So differential privacy doesn't do that. So what it does is the way I view it is to simulate privacy as opting out. So it says that the privacy doesn't mean that no new information about you can be learned. So privacy only means that the most you can do is to take your data out of the data set before I publish. So if you want, so for example, suppose I'm about to publish, I have data set D, and I'm about to publish a result AD. And if you your data is in the data set and you complain, then what I'm going to tell you is I'll just take out your data and I get D prime. I'm just going to publish the result D prime. So that if I'm publishing result on D prime, then you shouldn't complain because I'm not even publishing your data. So you don't really get to complain that your privacy is violated, even though new information about you can be learned, but it's not a privacy problem. So that's the view we take on differential privacy. But of course, we cannot quite achieve actually take out your data and publish that, because if I'm using that to protect privacy, I need to taking out everyone's data. So what we are doing is approximating, what differential privacy is doing is approximating that situation. So what I'm doing is similar to the case that you opting out, you take out your data, but not quite the same. So what this means is that differential privacy is good enough if we can apply this opting out argument, which happens is when the neighboring data set is defined such that for each data set D and each individual whose data is in D, then if we take out all the individuals' data, we get a D prime. That D and D prime should be considered to be neighboring. So then the differential privacy guarantees is that D prime should be viewed as the ideal world of privacy for individual X because we've taken out all of X data. So then we are simulating that. If epsilon is small enough, is suitable for the setting, then we believe the privacy is protected. And I have to say, I've seen many papers that use differential privacy in settings where we cannot actually apply this reasoning. So even though epsilon differential privacy is itself a clear mathematical precise definition, it doesn't mean that and it offers strong protection in this individual contact. It doesn't mean that for any contact it offers strong protection. So for example, if we are talking about human face recognition and each person have multiple images, and if you define differential privacy neighboring data set as just different in one image, then I don't think that's quite enough for protecting individual privacy. So you really need to define the neighboring data set as you're taking out all the image of one user. So, and there are many other contacts. For example, in social network data, you really cannot just take out a single edge relation. You really need to take out a whole user's data. So at least that's if it doesn't satisfy that, I think it might still be okay to do research in those areas, but I think at least that caveat need to be understood. So another reason that differential privacy is widely accepted is it has a number of nice properties. So the first one is if one algorithm satisfies differential privacy after we apply the algorithm, if we just take the output, we can do anything we want with the output. The output will still satisfy differential privacy. So while this is a natural property, for some property like a k-anonymity, this property actually doesn't hold. This invariance doesn't hold. So another sequential composability means that if we apply two algorithms, they both satisfy differential privacy, and we output both results, then we still satisfy differential privacy, just that the parameter adds up. So then this epsilon is known as a privacy budget. So these enable us to design very complex DP algorithm, so that we just need to make sure that every single step satisfies differential privacy. Then we know the whole algorithm satisfies DP. So that's a very convenient tool to use. And another composability is a parallel composability. That's if the data is partitioned into different parts and we apply different algorithm to the different parts, and then the privacy cost is kind of just a max of this algorithm. So we're going to see examples where the data is partitioned into many parts. So in the case of marginal tables, so then the privacy cost of that is just answering a single query. So so I mentioned that the sequential composition enables designing complex algorithms. So there's actually in recent years, there's a significant advance in this area, which makes the composability nicer. So the technical detail is actually quite complex. So I listed some of the papers here. But the high level message is if you have an algorithm that has many steps, let's say T steps, and where T is significantly large. So I would like to say at least like say 50 or larger, then the total privacy cost will grow proportionally to square root of T. So if you are answering a lot more, if your algorithm has a lot more steps, typically answering a lot more queries to gather more information, the cost doesn't grow as much. So I won't go in depth into explaining how that thing into giving some intuition on how that works. But essentially, if we are willing to tolerate a little bit weaker privacy, so known as epsilon delta privacy, then we can use these tools developed in recent years to achieve this significantly better composition property. So in general, the way I interpret this is this means that the big data can be quite friendly for differential privacy. So big data in the sense that we have data about more individuals. So if we increase the data set by a factor, say a factor of 10, so that generally means that we can answer most of the queries with about 1/10 of the original privacy budget. And because of this advanced composition property, so then that means if we want to answer similar answer queries at similar accuracy, we can actually answer 100 times more 100 times more queries. So then this is one way where big data make privacy easier. So another way where big data make privacy harder is if the data has if you have more data about one individual, for example, more attributes about one individual or more items about one individual. So then that make the privacy kind of more difficult in the sense that if you still want the same query accuracy, then privacy is harder. So so I kind of assume somewhat the familiarity with this basic mechanism for differential privacy. If you are not really familiar, then you can read down the standard literature on this. So one mechanism, one basic mechanism, Laplace mechanism, is if we want to publish the result of function f on dataset D, we will calculate the sensitivity, global sensitivity of the function. So basically, if I change if between a pair of neighboring data set, how much can this function change it? So you use that value, use epsilon. So this is, and then you use a Laplace distribution where the smaller the sensitivity, the less the noise. Similarly, the larger epsilon, the less the noise. You add that noise to the result, and this will satisfy differential privacy. And exponential mechanism can deal with non-numerical answers. So the Laplace mechanism is always dealing with numbers. So you add a random variable to a numerical answers. So exponential mechanism can be viewed as a generalization of Laplace mechanism to this non-numerical answer setting, where every answer is sampled with some probability, and this probability is determined by the quality of the answer, where you can define the quality. And then the sensitivity of quality will affect the probability distribution in which you sample the answer. So under differential privacy, some queries are easy to answer. So because easy meaning that with a small epsilon privacy budget, you can still answer relatively accurately. And counting query are I guess the standard example of easy queries. The reason is changing one record can only affect the answer to counting query by one. Some queries are hard because changing one record can dramatically change that the answer. So generally, those queries we can't really answer them accurately if we want to satisfy differential privacy. So max min is a good example. And then there are class of queries that are usually easy to answer in the sense that you can have a mechanism that works reasonably well. However, there exists pathological data set where the answer will be have significant error. So one example is a median. So usually median, you can intuitively usually median doesn't have it doesn't really depend on adding or changing one record that much. But you can come up with pathological cases where a median change dramatically when you change one record. So this means that we can come up with a mechanism for finding median that work well in practice, but we cannot prove any meaningful bound of utility because there will exist a worst case pathological data set where my algorithm is going to perform really poorly. So in this talk, we are going to use marginal table quite a bit. So I want to make sure that we all at least understand what a marginal table is. So we're dealing with relational data. So assume that we have relational data. So kind of equivalent way of representing the relational data is to use a contingency table. So here for this example, they're not quite equivalent because I'm changing the attribute, numerical attribute into buckets. But I guess just assuming that the input is already bucketized, for age, we just have two possible values, greater than 25 and less than 25. And income just have two values, greater than 100K and less than 100K. So then that means we can convert this table into this contingency table, which basically count how many records of each kind we have. So with 3 binary attributes, there are 8 possibilities. So this contingency table has 8 entries. So jumping slightly ahead of ourselves, this also illustrates the issue of kind of like an open challenge for differential privacy synthesis. That is, we don't really have very good method dealing with numerical attribute other than binding it this way. So so I think that that's an open question, is whether a better method can be developed for dealing with this. So given a contingency table, typically in a data set, there will be too many attributes. So for the data set that we are interested in, there will be too many attributes, so that representing the full contingency table is impossible. Even if they're all binary attributes, if we have more than, say, 40 attributes, then this will be too large to be represented. So a lot of time we want to consider marginal tables, which are counting number of records, but it consider only a subset of the attribute. So for example, if we consider only gender and age, it becomes this marginal table. We call this a two-way marginal table because it has 2 attributes. And this is a one-way marginal table. It has a single attribute. So we can get a marginal table while satisfying DP by adding Laplace noise to this count here. And because of the parallel composition, so this has the same cost as answer every single query. So then in some sense, marginal tables are the kind of the most efficient way of extracting information from a data set, because counting query already can be answered accurately with limited privacy budget. And here we are maximizing the kind of the effect of each query by answering multiple counting queries using the cost of one query, the privacy cost of a single query. So so kind of not surprisingly, the best algorithm for doing DP synthesis, the one that works the best in practice, actually all use marginal table as their kind of primary method for getting data from getting information from the input data set. So next I want to discuss 4 different settings for using differential privacy. So the first one setting is called the local setting. So this is also known as local differential privacy, or LDP. So in this case, we assume every user has data and there doesn't exist a trusted server. So then each user has to perturb their own data before sending to the server. So we're not going to talk about this in this talk after this. So another setting, what I call a single workload. So this means that, so all these, the other 3 settings here have a trusted server. So the trusted server have data, and in single workload setting, the server just want to publish one thing. So it could be a classifier. So you want to learn a classifier in a way that satisfies DP, but then only the classifier is sent out. Or he try to find the frequent item set, or we try to do say k-mean clustering. So, but essentially there's just one job the server want to do with the data. So then a lot of research on DP, especially in the earlier years, excuse me. So focus on developing differentially private algorithm for doing this each of the individual tasks. So in fact, personally, I've worked on each one of these. But the main limitation here is that you're using the data only for one thing. You cannot use it any for after you do this, you're kind of done. You'll use up your privacy budget. Doing anything more will kind of exceed your privacy budget. So the third setting is the interactive setting, which we assume there's a data curator which have access to the data, and then they will receive queries, and then they will answer them. So they receive one query, answer one query. They don't know what query will come in the future, and they just answer them as they come. And then there's this non-interactive setting where the server have access to the data, and what the server does is to kind of analyze the data and then publish something that basically describes the data set. And then any future query will be answered using this description. So the description is generated in a way that satisfies differential privacy. So then you can do anything to the description later on, so long as you don't touch the original data set anymore. So then one particular way of doing this is to publish synthetic data sets. So that, because then you can do any analysis you want, just like when before considering privacy. So in some sense, that's kind of the nicest setting, and which is the focus of this talk. So I want to talk a bit more about the interactive setting. So the setting is a trusted data curator have access to the private data set, and it receives query from the data users, and then it answers these queries as they go. So the question is, well, one challenge is anytime it answers some query, it's going to consume some privacy budget. So pretty soon, the data curator is going to exceed all the, to use up all the privacy budget it had. So then it's kind of the kind of stuck. So that's the main reason I think this interactive setting is not really practical. But it's motivated by earlier fundamental work on kind of lower bound result on data privacy. So these results are in the form of reconstruction attacks. It demonstrates that if you answer some number of queries accurately, then privacy is guaranteed to be destroyed. So the earliest, well, possibly the earliest result is this due to Denour and Nissan. So basically it says that if you answer a linear number of accounting query accurately, so accurately here means that the error is a small o of a square root of n, and this will destroy privacy. So because of this, the kind of the theory community, the earlier view is that we can only answer a sublinear number of queries accurately. So then just figure out how to answer those queries. So this kind of drive the interactive query answering, because if you are publishing non-interactively, then presumably that means you can answer many queries on them. But then because of this lower bound result, then most of them cannot be answered accurately. So then kind of what's the point? So I think that's kind of, at least implicitly, the reason that why people focus on this, at least in the theory community early on. But as we discussed earlier, there's some fundamental limitations that you are answering some number of queries, you run out of privacy budget. And the situation is exacerbated when you have multiple data users. So think about the US Census. Many people want to query their data, but you cannot assume that these data users are not colluding. So then you have to treat all of them together using the privacy budget. So very soon the privacy budget will be out, and some data user may not even be able to get a single query answered. So I think to kind of, I guess, in some sense mentally bypass this almost like a hurdle of reconstruction attack means that you can't really do things. You can only answer very limited number of query accurately. So I think there are several ways to view this. First is that some query you can answer that with a square root of accuracy, which will be acceptable. So in fact, this is a level of accuracy that can be achieved under local differential privacy. And I guess another kind of defense of this is you don't really have to answer all query accurately. So if you can figure out which queries are important, which queries are less important, so then and you are able to answer the important query accurately, then that's enough. So if you are published synthetic data set can answer an important query accurately, that's fine. Finally, what happens in practice is oftentimes we are able to answer some query with guaranteed accuracy. and those number of queries will be limited because because of the fundamental result. If we answer too many of them with guaranteed accuracy, privacy is violated. But for many other queries, even though we don't have guaranteed accuracy, so in the fact is that they can be answered with high accuracy most of the time. And here, this depending on the input data set. So for most of the data set, actually the query answers are very accurate, but we cannot provide guaranteed accuracy. There are pathological data set where the answer will be wrong. So then this doesn't affect the lower bound result because I don't have guaranteed accuracy for. But it's practically very useful because we can answer many queries with high accuracy in practice. So that led to the synthetic data generation part. So here is, I guess the schema of how this thing works. So there's a data curator with access to private data set. And then use this as input, it will generate synthetic data set that are similar to the private data set. And the generation itself satisfies differential privacy. Then after that, data user can use the synthetic data set any way they want without impacting privacy. So this similar, in fact, is actually not that easy to define, but generally in practice, it means that, well, in the literature, it means either for multi-dimensional range queries or low-dimensional marginals, what you get from synthetic data set is similar to what you get from a private data set. Or if you perform some tasks on the synthetic data set, it has good accuracy. For example, if you learn a classifier on the synthetic data set, it will have a good accuracy on, let's say, a holdout data set. So similar accuracy as from the original data set. So so there are like metrics like this people generally use in the research. So I want to argue that this is arguably the most important task when we are dealing with differential privacy going into the future. So basically, this is a problem we want to solve if we want to apply differential privacy. So if we want to apply differential privacy widely, so for example, U.S. Census Bureau apply differential privacy, but what the Census Bureau does is essentially publishing data. So what they need is basically generate synthetic data from the true data while making sure that the synthetic data is close to this. So U.S. National Institute of Standard Technology, so the organization which set like a crypto algorithm standard like AES, like SHA. So they ran 2 DP synthetic data challenges. So these are the only kind of challenge they run. So that means that they also recognize generate synthetic data is the key. So we participated in both of the challenges and did reasonably well, even though we, so I think we came, I think we were second place in the first one, and for different round in the second one, we finished in different places, second place, fourth place, first place. Anyway. So another advantage is if we generate synthetic data, then existing data analysis tasks can be performed with minimum change. So how do we do private data synthesis? So here's how I view this. So this kind of yellowish orange part is the kind of like synthetic algorithm. It will need to figure out what kind of query it should ask on the original data set. And then it obtain answers. And then using those answers, it will generate, it will compute the data distribution representation. And then from this representation, then they can generate synthetic data. So these, there are kind of these 4 steps where we can choose what to do. But the most important part is essentially how do we represent the data distribution? So I see 4 different approaches. First is we simply represent the full domain probability density. So in some sense, this is basically the full contingency table that we saw earlier. So some work takes that approach. And then they're using probabilistic graphical model, neural network, generative model. And our own approach actually doesn't use a specific representation. It just uses a set of low dimensional marginals. So let's first look at this full domain distribution. So yeah, so basically the internal representation is the distribution of all attributes, like the full contingency table. And the example using that is this paper. The mechanism, they call it multiple weights update rule with the exponential mechanism. So this paper assumes we have a set of query we want to answer accurately. And it will start with a uniform distribution over the whole domain. And then it will repeat a number of times. Every time it uses the exponential mechanism to choose the query that has the largest query error given the current distribution. So if we use the current distribution to answer the query, compare with using the true data set to answer which query has the largest error. So then we find the query. So this step using exponential mechanism to satisfy differential privacy. Then we obtain noisy answer to the query. And then we update the distribution using this query answer. And this uses what's known as the multiple update rule. So, so the problem of this approach is when the number of attributes is large, when higher dimensional data, you can't even represent the joint distribution. So that paper has some primitive way of splitting the distribution. Basically, just assume, say, this part is independent from that part, but that doesn't really work well for practical data sets. So another approach in the literature is neural network generative model, using, for example, again, generative adversary network. So so I guess this is a kind of because GAN has been shown to be effective in generating things like image. So people naturally think that we can use this to generate synthetic data. To basically be able to use this to represent the distribution of the data, and then we can sample from it. So, but it doesn't perform well empirically for tabular data. For example, there are GAN-based methods participate in the NIST competitions, but they perform pretty poorly compared to the other methods. So personally, I think there might be two reasons. One of them is that the kind of query GAN uses do not use privacy budget efficiently. So there are different ways of training GAN, either by adding noise to gradients or to using something with the labels. But none of them use the privacy budget to get a whole lot of information from data set compared with the marginal tables. You use a marginal table, you are getting a lot of information from the data. But using GAN, not so much. And also, when you use marginals, generally you select which marginals you query. So then the ones you chose, the marginal you chose, you get very accurate information. So there's a degree of control over what information is preserved. So remember, if we want to satisfy privacy, we have to give up on something. So using marginals, you can select which you keep, which you give up. But you can't directly control that using GAN. So there is one paper that kind of combine marginal with GAN. So this is known as CT GAN. The paper is listed here. So it gets all one-way marginal. So it at least preserve all the one-way marginal information. And then it also use some other trick. So the result, I think, at least is better than other GAN approaches. But I still don't think it's as good as the state-of-art approach based on marginals. So, so remember, the challenge we say here is we have a high dimensional probability distribution here, and we can't directly store it. Well, in some sense, that's exactly what probabilistic graphical models are designed to do, is to represent these high dimensional distributions with not that with a lot less space. So so here I listed two papers. So they either use a directed probabilistic graphical model, Bayesian network, or undirected, known as the Markov random field. And I guess the main challenge is to decide how to learn the structure of the network. And once you learn the structure, the parameters are typically just learned through marginal table. So it's the structure learning, there can be improvement here. And I think the earliest work of PrivSyn doesn't perform as well, but there are later improvements in that. So once we have the PGM, then we can just sample from this to generate data. So these are some limitations on the specific approach we look at here. So I'm not saying this approach cannot be addressed in other ways. So there may be ways to address them in the probabilistic graphical model framework. But this kind of partially motivated our own approach, which we call PrivSyn. So the basic idea is we do not have a representation of the distribution. We only use the marginals we get from a data set. So there isn't this step of generating a data distributed representation. That's not there. So we directly synthesize data from the marginal table. So the information we have are low dimensional marginal. So in this, I listed two papers here. In the 2014 Sigma paper, we developed techniques to make marginals consistent. And then in this later paper, building on our experience participating in the NIST contest, we developed ways to synthesize data from the marginals. And compared with the PGM, this can be viewed as a non-parametric method. So basically, we don't assume a model to learn the parameter. We just, from the marginal, the raw information, we directly go to synthetic data. So the first challenge is how to choose a set of marginals that capture useful information. And the second is how do we generate synthetic data set from those. So I'm just going to give the high-level intuition for how to select the marginal. So essentially, we want to select a subset of all the two-way marginals. So this was we applied this to fairly high dimensional data. So data with over 100 different attributes. So that's why we only consider two-way marginals. So in other settings, then maybe we also consider three-way marginals. So what we want to do is we want to select the marginals, but when we select the marginals, we need to add noise. And when we don't select the marginal, so we will have to rely on other things to construct their dependence. For example, if we select A, B, and AC, but not B, C, then we do not have direct information about how B and C are related. All we have is how B and C interact through other attributes. So then if B and C are highly correlated on themselves, then there will be error. So what we do is we can calculate this dependency error. So then what we want to optimize is the sum of noise error and dependency error for all of these marginal. So this is abstractly the optimization problem we want to solve. But solving it actually is NP complete. So we use a greedy algorithm to do that. So I will skip the details. So that's the part of how to choose a marginal. And also in practice, if you have when you publish private data, oftentimes you have similar data. So which attributes are correlated so that you need to publish their joint marginal are also can be obtained without privacy cost. So in that case, it'll be a manual effort to design the marginals, and then you just need the privacy budget to get the noisy margin. So selecting marginal can be done in other ways. And given the marginals, the way we generate the data set is we start from a randomly generated data set. So so if you want some number of attributes, you want 1 million attribute, 1 million record, then we will randomly initialize 1 million record, and then we will repeatedly query use the marginal to update this data set. So we look at the two-way marginal using attribute A1 and A2. So then that tells us some number of records, some fraction of records should have this particular value of A1 and this particular value of A2. If we have too few of them, we'll need to increase record having that. If we have too many then we will reduce that. So basically we massage the data set to make it closer to the marginals. So we tried different things in trial and error in how to do this thing. So we iteratively go through this marginal multiple times to gradually massage the data so that it will match all of these marginals. So that's the high-level idea of this method. So while we try something, I'm I'm pretty sure there are probably we haven't really exhausted what are the possible way to do it, and we haven't really found the optimal way of doing this. And also recently, I realized this generating data when given marginals is actually also studied in other fields. So, for example, in civil engineering, especially transportation engineering, there are actually a bunch of papers studying that this problem. So maybe some of that can be used. So in the written paper published in last year's Usenet Security, so we did some experimental comparison of our approach with other methods, including the Bayes network and the Markov random fields. So roughly what we find is that on pairwise marginals, all these methods are similar. But on range query and classification accuracy, so basically we learn a classifier on our synthetic data and how well it works on the validation data. So what we find is that our method perform better, but I guess there might be ways to improve this PGM-based method to also work better. So that's certainly to also work maybe similarly well. So that's certainly possible. I don't think the case is closed on the using graphical model versus not using it. And we also find that our ways of choosing marginal is better than the original way in Bayes of choosing marginal. So the original way in Bayes paper use query that are fairly high sensitivity, so it's not very accurate. But that can also be changed. Yeah, and also what we find is actually even this choosing marginal, even satisfy privacy, actually it works reasonably well. So similar to do it without the privacy constraints. Okay, so that's kind of the summary of what we have done. So what are the open problems? So I think there's a probability graphical model versus our direct approach. I think we haven't really understood the pros and cons of this two approach. So both methods extract information from input data set using marginals. And if you use PGM, then you will use this marginal to build the PGM, and then you will sample from there. And here we directly use marginal to synthesize data. So I can see high-level reasons that one method is better than the other, and vice versa. I don't really fully understand what is the trade-off of using it. And also, both methods can be refined in how to select marginals. And in the case of our approach, how to synthesize data sets from marginals, maybe work in other area can be applied. Idea in developing other field can be applied here, but I look at some of them and haven't seen very promising idea. So another thing that I view as open problem is there's probably better ways to deal with numerical attributes. So in the current approaches, numerical attributes are basically being into categorical attributes, and then we just use the machinery for categorical attribute to handle them. But we lose the order nature of those values. And also, a lot of time, the granularity of binning will have a big impact on the final accuracy. And it's really kind of difficult to try to choose that for every attribute. So I think there may be better ways to handle numerical attributes, exploiting this order nature, but it's not quite clear how to do that. So finally, I want to talk a little bit. I guess this is a little bit like I guess you can say this is a little bit like a ranking. But I think there is a kind of important gap here between theory and practice. And the gap is kind of paradoxical in the sense that for complex tasks in differential privacy, so this is limited to differential privacy. So any algorithm that have a theorem proving the utility bound actually perform poorly in practice. So then conversely, so what I'm saying is any algorithm that performs well in practice has no proof of utility bound. I guess this is a ranking in the sense that sometimes, sorry, Can people hear me?
Yes, okay.
Yeah, sorry. Yeah, my computer shut down accidentally. Okay, so okay, so let me just let me just use the example to illustrate this gap. So this is from the MWEM paper, which uses full distribution to represent data. So it had this. So this is the algorithm that I briefly described earlier. So start with a uniform distribution, iterate t times. Every time you select a query, using exponential mechanism to select the query with the most error, and then you get the answer to that query, and then you use that to update your distribution. So here, this update doesn't really make your distribution exactly match it. So just get it closer to that query. So then, given this algorithm, we have a theorem which proves that this algorithm produce a data set that have a good answer. So, but the problem is actually this algorithm is really, really bad. So for a number of reasons, and actually the author kind of know about that. So in the next, so the section says, well, several ways to improve the performance, the algorithm, but when you improve the actual performance algorithm, it's at the expense of the theoretical guarantee. So basically, once you make changes to make the algorithm perform better in practice, you no longer have the proven utility bound. So here are some of the changes. So the previous algorithm is when you keep getting new query, updating the distribution, but in the end, you actually don't use the last distribution. You actually average all the distribution. So you start with uniform, which has no information, and you gradually improve it until the end. But when you return, you actually return the average of all of them. So obviously, this is pretty bad because you are using this uniform distribution played an important role. In the earlier part of the update, the data distribution is still pretty bad. So instead of using average, use only the final distribution. So in some sense, if you care about practical performance, of course you're going to use the final distribution, but then you lose the access to the technical tools to prove things. So okay, so I'm going to answer the query after I'm done with this. And then also this update just changes the distribution once. But in reality, what you want is you keep running over the against all queries, and then to make sure that your the distributions answer to all query are similar to what you get. So that's what this is second. And then there are some other changes. But essentially doing these things that are obvious that you should do in practice, but then you lose the ability to prove. So I think the possible reason is practically effective algorithms are very complex. Therefore, they're difficult to analyze. So you simply cannot prove anything because the algorithm is too complex. So this was the case in the previous algorithm. And also, any provable bound must hold for worst case data set. So then this means that even if you prove something, the bound is actually not very meaningful. So in fact, that the bound in the previous paper wouldn't be meaningful because we already know the algorithm performed really bad. So, but there's still a proven bound. So that the only thing it means that the bound is actually not really useful. Okay.